Okay, so last lecture, we were starting our exploration on chapter 2. And we got through, if you remember, we had 4 major subdivisions in this chapter, right? We had effectively, how do we store data as subdivision 2.1. The next subdivision is 2.2. How do we represent integers inside of our system? The follow-up of this chapter is going to be how we do arithmetic on integers. And then finally, how do we handle fractional numbers? How do we do our floating point numbers? Today's lecture, I'd like to get through all of 2.2. And then the third and final lecture on this chapter will be on Tuesday, which I'll do the arithmetic logic and then also floating point numbers. I'll try to consolidate those into one lecture. And so the next lab that you have covers these concepts. I'm going to unlock that for you all tomorrow so that you can start working on it based off of what we've already covered, based off of the readings you could do in the book, and based off of the lectures that we'll continue to have next week. Okay, so here I want to then move on to integer representations. So there's 2 ways that we can represent integers, encode integers using binary sequences inside of our system. We can do unsigned encodings, and we could do 2's complement encodings. 2's complement encodings you can think of as a signed form of encoding. And so the big distinction between the 2 is that unsigned numbers include only non-negative numbers, right? We could think of that as our whole number set. And our 2's complement is a mechanism that allows us to capture encoding both negative and non-negative numbers. So we can get negative, 0, and positive numbers in those representations. So let's explore. Let me get here. So let's explore these a little bit more in depth. So in terms of our integer or integral data types, the different representations of our data types in terms of our actual system is based off of 2 different concepts. It's size, how much encoding space in terms of our bit vector, our binary string, are we going to allocate for our numerical representation? And the other is, what numerical set do we want it to be defined as? Does it have to have a sign? Is it going to be a signed representation, so it include all negative and positive representations, or is it going to be strictly positive and 0? So non-negative is the more accurate term for that. And of course, when we talk about this at a system level with C, that means there's going to be a key word that allows us to do each one of those. So for instance, the key word we use for an unsigned, well, we'll get that into another slide, but clearly well, I'll wait until we get to the slide. I won't sidebar myself. Okay, so the result, though, is once we know that the size of the binary string, the amount of bytes we're allocating to represent our number, and the subset of integers we're talking about, whether it's the whole set of numbers or the integer set of numbers, the whole integer set of numbers. Shouldn't use the word whole set of integer, because then that's just, whether it includes negative numbers or not is going to really depend on what your minimum or maximum values are. So this chart right here, this table just gives you representations based off of the keywords I mentioned last slide. So for instance, if you have a car, and it's if we think of it as being a signed value means it can include negatives, then we can have a minimum value that goes into the negatives, right? If you have something that's unsigned, then the starting value is going to be 0. And that's going to affect the range of values you have between min and max. And so by default, things are signed. And so if we want them to be unsigned, we have to use the keyword unsigned to shift the range of values so that they're non-negative. And in this, you could see how small and big each of those get. Okay, so let's talk about unsigned integers as bit vectors. We're going to start very simple and start our build ourselves into complexity. There's one of two ways that we can mathematically express a bit vector. We can either just use a value with the arrow over whatever the label is. So let's say I have my bit vector x. I can express the entire bit vector by using the arrow notation on top of it. Or I can expand the vector out at a per element basis. So in this instance, you see on the under here, I can see the individual bits. So and my bits are going to start from the least significant, which is the rightmost bit, all the way to the most significant, which is going to be my bit that's at whatever the width is. Okay, so it's important to understand the two representations when we start breaking out any kind of mathematical definitions. That way, you know how to think of. So the vector expression just represents all the bits as if it were one contiguous thing. Okay, so with that said, let's now think about our unsigned integers in terms of a binary notation. So each bit that we have either has the value of 0 or 1. If it's a 1, then inside of that vector, we would denote at 2 to the power of I, where I is the instance it's a 1, will be included in that numerical value. So we know how big or little our numeric representation has to be based off of where the ones populate, right? We don't care about where the zeros populate. So you know how much space you need to reserve for your integer value based off of that encoding. Like the ones are the important part. That's the part that we're looking to kind of to indicate. We're going to define a function.
Oh, if you're gonna, maybe you're gonna explain it the next one. I just haven't gotten that far. I'm in Calc 1 right now, and so I'm not familiar with that notation. Is there anything that I can look up to?
Which notation is it in particular?
Summation.
Oh yeah, sure. Yeah, so I'm about to go ahead and kind of walk through this. So we're going to define some functions formally, mathematically, and then we're going to talk about it notionally so that it makes sense in terms of an English-like explanation. So the first thing we're going to look at is the function, the mathematical function that is our B to U function, short for binary to unsigned. Bit vector, when I say binary, I mean in particular my binary sequence for my bit vector, so that we can translate that into our unsigned integer, so a non-negative integer value. So notice I have a subtype there of W. The subtype W represents the width of the binary string. Now, typically, you might also hear that as length. So we'll say we'll have a length of the binary string using the word W, which represents width. I feel like, you know, it's 1D. So length, width, in this case, it's interchangeable, but it's kind of confusing, I think, to use the two different terms, but the book does. So it's probably because L can look like a 1. So W's are good for that. Okay, so inside the parentheses is going to be the bit vector that we're going to pass in. Hence, you can see we have the arrow over it. So we're passing the entire bit vector into this function. Now, the beautiful thing about the notation we talked about is we can think of a vector either as a full, as an expressive of just one identifier, such as this X with the arrow over it, or we can think of it as unpacked and as a per element basis. So what we're seeing on the right-hand side of this notation is now going to be X. And when you see the sub-I, the subtype I, so moving past the sigma notation, I'm going to look at this part right here. That's accessing at a per element basis each of the items inside of our bit vector. Okay, so our sigma summation just means we're going to go ahead. You can think of this almost like a for loop. So we're going to iterate over every element inside of the bit vector and do this action, this process on it. So at the bottom of our sigma notation, we're going to put the starting term. And at the top of our sigma notation, we're going to put the ending term. So starting at I, and you can think of I in this instance almost as if it's an index of. So starting at index 0, we will iterate until we get to W minus 1. So the length minus 1. And so effectively, this is the same way we would do a for loop in computer science, because if our index starts at 0, then the last element of our bit vector is going to be the length minus 1. So this is just indexing, providing an indexing arrangement where we're indexing into each one of these. In sigma notation, what that does is for each one of those, like, so we would do this for I equals 0, I equals 1, I equals 2, I equals 3, all the way until we get to W minus 1. And we take all those individual terms and we add them together. So what are we adding together? We're taking whatever the value of X sub I is. So in this instance, this is a scalar value, right? It's going to be a scalar value of 0, 1, 2, 3, 4, 5, 6. And then we're going to multiply to that the 2 to the power of I. And so that's going to either make it a 0 or a, well, it depends on what our I term is there. But what that's going to do is, and I wish I should show you an example of this. What that's going to do is, remember previously, did I show the representations of when we do our computations? We can have like 2 to the power of 0, 2 to the power of 1, 2 to the, and then you have your scalar term on top of that on whether it gets zeroed out or not. And then that builds out your integer because you sum all those together, right? Like, so for instance, when I have the binary string of 1, 1, 1, what value is that? 7, right? 7. And how do I know that? Because I have 1 to the power of 2, 1 times 2 to the power of 0, plus 1 times 2 to the power of 1, plus 1 times 2 to the power of 2. And so if I then kind of stretch that out, 2 to the power, so we haven't zeroed any of those terms out. So that's like saying 4 plus 2 plus 1 is 7. If I ask what's the unsigned integer value of 5, I'm sorry, the unsigned integer value of the binary string 101, it would be, the one way of expressing this in this mathematical definition would be 1 times 2 to the power of 0 plus 0 times 2 to the power of 1 plus 1 times 2 to the power of 2. And so my 2 to the power of 0 term is there. My 2 to the power of 2 term is there, but I've zeroed out my scalar value, zeroes out the 2 to the power of 1 term. So that means the 4 and the 1 counts, I add those together and I get 5. Does that make sense verbally? Because I don't have a slide that I'm walking through, so you got to just pay attention. I'm pretty sure we've seen that, and I think I have slides that will articulate that as well. But that's exactly what this is doing. This is just expressing mathematically that formula of where you take 2 to the power of where that digit is in the binary sequence, and you're either zeroing it out or multiplying it by 1. Because remember, we're indexing into the binary string. So x sub I is only ever 0 or 1, right? It can't ever be any other scalar value. If it's 0, then we ignore that bit, or that bit is zeroed out. And if it's a 1, then it is what the 2 to the power term is in terms of that where that it falls in that sequence. Does everyone understand what this function does now? Let me see if I have an example. I hope I did an example on this. Oh, yes, I did. This would have been way easier than me trying to just state it verbally. I like visual examples. So here, this is an example of our B to U function. So here we can see we're going to map from our bit vector to our integers. So here, let's look at these powers again. 2 to the power of 0, mathematically, we know that's 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8, right? So we can see the growth rate. We're going to represent that visually so that we can kind of see how, when we sum this together, how it starts to expand into an integer value. Okay, so let's invoke this function. Now, I said the subtype of 4 is how many characters, how many elements, what is the width of our binary string. So in these instances, we're passing in a binary string sequence of 0001, 0101, 1011, and 1111, right? So all of those are going to be 4, have a width of 4, a length of 4. And so that's what's going to define how many sigma summations we do in our original mathematical function. So the way that this unrolls is we would take that 0 element, the least significant bit on here, right? We're going to unpack it. So we're going to grab the actual value. It's a 1, and we're going to multiply it by 2 to the power of 0. Then we're going to add to it 0 is the next one in here to 2 to the power of 1. And then we're going to add to whatever result that is to 0. That's the next value that falls in the binary string to 2 to the power of 2, because we're at the index value 2. And then finally, the last index value, if we start at 0, is going to be 3. So 2 to the power of 3 times 0. So if I resolve this mathematics out, it's going to be the equivalent of 0 plus 0 plus 0 plus 1. So this is a representation of 1. So this is just the very formal mathematical function of what you probably were just mentally doing in your head, right? Where you're counting the place of where the ones were occurring and just doing a multiple of 2 there. And then visually, we could see how that looks here. There was only 1 bit that was a 1, so we could see this is the only one that counts. Let's look at one that's a little bit more interesting. Let's look at, say, for instance, 0101. Here, we're going to take the term at index 0, and that's going to be a 1, so that's going to count. The term at index 1 is going to be zeroed out, so that's not going to be part of our summation. The term at index 2 is a 1, so we'll actually resolve 2 to the power of 2 at index 2. And then finally, the term at index 3 is a 0 in that binary string, so we're going to zero that out. So that's going to result in 0 plus 2 to the power of 2, which is 4, plus 0, because we zeroed that out, plus 1, 2 to the power of 0. So if I visually wanted to see that, this is one of my bits that resolves to 4 units. And this is another one of my bits at the least significant bit that resolves to 1 unit. I sum those together, and I get the value of 5. Okay, let's look at this. 1011. I'm just doing the same thing, right? The same parsing. We're just zeroing out different terms and adding different terms. And you can see visually when we do that here. So these where the most significant bit is set to 1, that's going to contribute 8 units. Plus, let's look at the last one. Plus, we're going to go ahead and contribute 4 units. And then we're going to contribute 2 units. And finally, we're going to contribute 1 unit for a total max value of 15, all across a binary string of 5 bits. So this is the mathematical definition of how we can go ahead and translate our binary sequence into an unsigned integer. Does this make more sense? Okay. So let's talk about unsigned integer ranges and how those relate to the widths of our bit vectors. So as we stated earlier, our least value in an unsigned bit representation is 0. That's when all your bits are toggled off, right? 0, 0, 0, 0. So we start counting at 0. The greatest value we can have is when all of our bits are toggled on as 1, 1, 1, 1, 1, 1. That means that if I wanted to define a function to find what is the unsigned max for some given width, and here you could see how I might express that mathematically here, u max sub w, I could define that as 2 to the power of w minus 1. So thinking back at this prior term, let's go back to this slide and just check that mentally using this as an example. Because the very bottom call to this function, we passed in all ones. Well, we could say that should be the same as 2 to the power of 4 minus 1. 2 to the power of 4 is 16, minus 1 would be 15. And of course, the reason why is we start counting at 0. So our rollover term is going to be that. And so that's how we define what our function is based off of how many bits. So just looking at how many bits are part of our bit vector, we know what the max value could be, and we know what the min value could be. And we know we can encode some unique value to every other number between a min and a max. How do we know we have a unique encoding? It's because when we define this function, the reason why we define this function mathematically is that we can then lean on mathematical definitions and rules to state things with authority, with veracity, with a force of truthfulness. Okay, so once we've mapped this definition from notional to mathematical, we can state the function we've created is a bijection. Does everyone know what a bijection function is? So a bijection function is a mathematical term that represents a function that maps a value from x to y in the form of y is equal to f of x. So given some x value, we pass into our function, it produces a y. And given some y value, we can pass that into the inverse function and it produces back that x. It means there's a one-to-one correlation. And if you might recall, one of the special definitions of a function, a mathematical function, not like a computer function, not like a code function, but a mathematical function, is that given some input, it's deterministic. It always produces back the same output, right? You can't, like, for instance, if I made the function x plus 3, right, and I put in 5, I'm only ever going to get back the value of 8, right? I can't get back anything else. And so when you have a bijective function, you know that there's a one-to-one correspondence, a one-to-one mapping between both elements of those two sets. And we're talking about two different sets that these functions operate on. One is a binary, a bit vector, right? And the bit vector's representation is where are the ones and zeros oriented inside of those strings. And the other is the unique integer values between our min and max value. So based off of the fact that there's an inverse function, that this is a bijective function, we can create some other function that we can call unsigned to binary, or U to B, that also works on a subtype W, which is the width of our binary string, where we pass it in an unsigned value and we could retranslate that into a bit string. And that bit string will look the same if we pass it to the B to U. And the range of that is going to be 0. It's going to follow the same range that we mapped in the other slide. Okay, so as long as everyone agrees it's a bijective function, then we don't have to manually do a cross-reference on each binary string to a number, right? We can use our function to arbitrarily define that, and we can rely on that. So the binary string can now be however many digits. It can be 1,000,000 digits long, and we know how many values we can encode with that. Okay. We're done temporarily for unsigned numbers. Let's move on to signed numbers, because unsigned numbers are easy, right? Unsigned numbers are the ones that you learn how to start counting in binary, starting with the 0 digit and the 1 digit and the second bit where it's another power of 2. So you can do 2 and 3, and then you can do your combinations. As you keep adding bits, you start getting more and more combinations that you put together. But how do we add into the mix negative numbers? Let's talk about not just negative numbers, just what it means to be a signed number. So the 2's complement form, and I'm sure you probably covered this a little bit in assembly already, is used to represent our negative positive values, which is what we're going to call a signed value. And so the basic notion, and this isn't just true for 2's complement, this is the basic notion for signed values in general, is that we prefix a value, a numerical value, with a sign, which allows us to then interpret that value as either being positive or negative. So for example, if I had just the value of 5, if I did +5, then that indicates that's a positive value. If I did -5, that indicates a negative value. If I don't put a plus or minus sign in front, the default value we ascribe to that is positive. Okay, so that same notion of how we just apply a symbol, a plus or minus in front of a value, a numerical value, to now define our negative and positive space is the same way we're going to apply a sign onto our binary space, into our binary string. Because the exploitable concept on how signed numbers work already is that it's a 2-state set. There's only 2 states that you prefix in front of your signed number, plus or minus. So that makes it super easy to capture that behavior with a binary string. We can do a binary representation of anything that's all just 2 states. Okay, so let's talk a little bit more about what it means for the 2's complement form and how we can kind of exploit it, what it means to be a complement. The 2 complement is defined by interpreting the most significant bit of our word, of our binary string, of our bit vector, as the sign bit. So that's the symbol that represents whether it's a plus or minus. So if I want to define some function, b to t, where t in this instance is 2's complement, and the subtype that we're defining this on is going to be the width of our binary string, of our bit vector, is going to be, so we were talking about the function. Okay, so the mathematical expression of our function to be able to translate between our binary to our 2's complement is going to be as such. Suppose we had that bit vector x, so we'll call it x, and so we're going to express that bitwise, where our least significant bit is going to be at the subdomain 0, and we'll go all the way to w minus 1, right? So you can effectively think of that as a list or an array, just like the prior example. When we go to invoke this function, given whatever the width of our vector is, and we pass in our vector, we're going to do another sigma notation here. But notice we're going to add, before we do the sigma summation, we're going to add at the most significant bit. So 2 to the power of w minus 1. That's going to be the very front of the very first element that we would read on the leftmost element. Let me use that. The leftmost element of the binary string is going to be toggled as either minus or positive based off of the state on whether it's a 0 or 1 here. And then we'll add to that the summation, just like what we saw earlier here. So this part is exactly the same. The only thing we're toggling is going to be whether this is different or not. And so the idea here is, let's think about what's happening here. Effectively, we're going to multiply at, so when we index into the leftmost element, if it's a 0, let's say it's a 0. So it would be 0 times 2 to the power of whatever that is, right? Like if it's 4, it's 4, right? But if it's a 0, we zero that out. And that means our negative term is getting zeroed out, which means that's going to be a positive. Now, suppose that it was a 1 that's at the leftmost element, the most significant bit. Then we're going to take that 1, which has the negative sign in front of it, and we're going to multiply it to whatever it normally would be, right? 2 to the power of whatever index that's at. And so you notice how by having the 1, we create a negative context for the integer representation, whereas if it starts with a 0, we cancel it out and it's going to become a positive context. Does that make sense? We'll see an example if it doesn't make much sense. Now, that's gonna have a consequence. So the most significant bit not only carries the sign, but it carries kind of a weight that gets applied then towards the integer conversion, the integer translation. And we're going to graphically see how that's going to impact the range of numbers we have access to, and how we can use this, how we can exploit this concept to eventually build to being able to do arithmetic with some of these representations, why they're complementary to one another. Okay, so let's go back to this example where we can visually see. We get we move away from the pure mathematics, and we have some nice visual representations. Here I have my b to t function, so my binary to 2's complement. And so here, just so that we can define what our values are, we're going to have the blue represents positive values. So this is going to be a with a 4, which means our most significant bit is going to be at I equals 3. It's the leftmost. So that can either be zeroed out, where it's not a contributor, or it could be -8, where it's actually taking things away from them. So it's gonna drag you back. And so the blue represents a positive contributor. So this is our negative weight, and the blues are our positive weights when we talk about our summation game. And so our blues can either be zeroed out or they can positively contribute, right? So the only thing that can take away is the most significant bit. Everything else is going to be part of the summation. Okay. With that said, let's look at invoking this mathematical function, rolling out the sigma summation, simplifying it, and seeing how it visually stacks up to these representations of the blocks that we have here. So on the binary string of 0, 0, 0, 1, I can re-articulate that as the same way as we did before, right? At least before we get to the most significant bit. So here we're going to have all of our terms are going to be zeroed out except for the least significant bit. So I'm going to do 1 times 2 to the power of 0. Then this second term will get canceled out. This third term will get canceled out. And then the most significant bit, which carries the minus sign, is going to get canceled out. So when I sum those together, I'm going to result in the integer value of 1. Okay. Let's look at the same computation, and this is going to look very similar to our unsigned computation from before, where of 0, 1, 0, 1, the most significant bit is 0, so we know it's not going to be a negative term, right? So we're going to have our 1 bit, we're going to zero out 2 to the power of 1. We're going to resolve 2 to the power of 2, so that's going to resolve into a 4, and then 2 to the power of 3 that carries the minus value as well gets zeroed out. So it's going to give me a positive 5 when I sum those all together. Okay, let's actually now look at how we can now represent negative values in this scheme. I'm going to take the 1, 0, 1, 1. So just looking at this, knowing this is 2 complemented, the most significant bit is a 1, we know it's going to contribute a negative value, which means it's going to take away the most significant bit weighs more than all the other bits behind it, right? Would everyone agree with that? If I have 3 bits, that's 7. If I have 4 bits where the first one is 1, all the other ones are zeroed out, that's 8, right? My most significant bit is more valuable than all the ones behind it, which means if it's negative, I'm going to resolve into a negative number. Okay, with that said, I have 1, 0, 1, 1 as my binary string. So that means we're going to resolve 2 to the power of 0. We're going to resolve 2 to the power of 1. We're going to zero out 2 to the power of 2. And we're going to resolve 2 to the power of 3. And that's going to be a negative term. So let's see how that stacks up. 2 to the power of 0 is 1. So that's our 1 blue block here. That contributes to our summation. The next one was 2 to the power of 1, which is 2. So that's the next blue block. So those together are going to resolve to 3. But then I'm going to have 8. That's going to resolve my 2 to the power of 3. But I'm multiplying a minus 1 in front of that. So that drags my 3 back by 8 units. That's going to make it minus 5. And so, in fact, if I go all 1s, let's see how that resolves. 2 to the power of 3, we know it's going to be negative, right? We know that that's going to resolve to be minus 8. And if I took a sum of the digit at the element at the second, first, and 0 index of that binary string, that's what? That's going to be 1 plus 2 plus 4. It's going to be 7. Minus 8 plus 7 is going to be minus 1. So my representation for minus 1, it makes sense. It's going to be when everything is all 1s, right? Because I'm taking the most significant bit is toggled on, which is my negative contributor, but all the positive contributors are also toggled on, but there's a difference value of 1 unit. So the encoding value there is minus 1. So this is an interesting concept, though. Think about how different that distinction is, that encoding is from our unsigned numbers. We're going to talk about that for a little bit. Okay, so let's talk about the similarities and difference between when we define our function from binary to 2's complement versus binary to our unsigned. We can say that when the most significant bit is 0, they're identical to each other, right? We saw that in the examples. We can also say when the most significant bit is 1, then we're mapping to different values. 1, 1, 1, 1 in an unsigned encoding is as high of a value you can have because they're all summed together in a positive fashion. Whereas 1, 1, 1, 1 in a 2's complement gives you the value of minus 1 because the most significant bit is bringing you down. It's producing a negative consequence towards the sum result. Maybe consequence isn't the right word, but it's bringing down the summation beyond to the left of 0. Okay, let's talk about ranges. So signed integer ranges and widths. We talked about this. Yeah. So we know that we had stated earlier that the range of unsigned values are between 0 to, what was it? It was 2 to the power of w minus 1, right? So what is the range? Now that we've introduced our negative terms, what do you suppose our range is for 2's complement? Well, the number of encodings for a binary string hasn't changed, right? The combination is the same, but by introducing the sign bit, that's effectively almost going to have what our range is, or from the positive side, it drags it into the negative side. So you could think of what we're doing as shifting the range, starting from 0 to shifting that range all the way until where our minimal value, our T-min value, can be defined as minus, so we're applying a minus in front, 2 to the power of W minus 1. And that means our max value is going to be 2 to the power of W minus 1 minus 1, because we also have to encode 0. So there's not a one-to-one complementary there. You're actually going to have one more. You're going to have just as many non-negative terms and negative terms, but you're going to have one more negative term than positive term if you don't count 0 as a positive unit. And that's just what happens when you split things in half, and the halfway split is going to be between 0 and your negative values. So we can actually prove this in this example here. If I do if I go and look at my bit by binary to 2's complement, I can see if I toggle just the most significant bit on and then everything else is zeroed out, it's going to be my minimal value of -8. And then my most positive value is where my most significant bit is 0 and everything else is toggled on. That's going to be a 7. Okay, and just like with unsigned, my unsigned function, my 2's complement also is bijective. That way I know it guarantees a unique encoding for every value from the binary string, starting from the least size string to the greatest size string. So the string can be arbitrarily large, and I can guarantee that I can represent a unique value in the integer space, the integer set from that, which is super important for mapping, right? For hashing values. Okay, so here are some hexadecimal values, which are another way of expressing our bit vectors, our binary strings, and how they would then resolve into both unsigned and signed values in terms of what their maximum values are. So like my unsigned values, the max, versus my minimal value for 2's complement and my max value, and what my expression, what my constant value of -1 versus 0 would look like. Okay, so let's talk about why it's important to understand how we're encoding our unsigned values from our 2's complement value. Let's talk about the consequences with that in C. Because one of the things that the C programming language will allow you to do is cast between the two forms. And so as a general rule, the way that C handles this conversion is it maintains the bit vector and it changes what the expression is. So for instance, looking at the sample code here, let's say I want to cast from a signed value into an unsigned value. So a signed value is one that we're going to put a minus sign, because that's when it's meaningful, right? That's when the representations, the interpretations start to change. So suppose I have the minus value of -1, 2, 3, 4, 5. And then I force a casting of that, and I'm going to save that into an unsigned short. And then I'm going to print both those out. I'm going to see that the binary sequence of this is the same. This is just the 2's complement versus the unsigned interpretation. But the translation is going to, it maintains the bit sequence. And the same is going to be true with casting between unsigned to signed. So it's not changing the values that are in the register space. It's just retranslating how we're interpreting that value. But be aware, if you're doing any computations between signed and unsigned numerical values, that they get interpreted differently. So when do they start to mix and match? You should be aware of that. In fact, we'll talk about that in just a moment. And here we have 2's complement to unsigned. So suppose I wanted to go ahead and convert or interpret. So if the C programming language is converting, allowing us to cast between our unsigned and signed representations, we should understand how it's doing that. So this is the mathematical definition of defining a function that we will call, here we go, T to U sub W, where W, of course, is the width of our binary string. Here, it's really easy. If X is greater than or equal to 0 inside of our 2's complement, then we keep it the same. However, if our X is equal to, and again, what we're passing in here is a binary string, right? If X is X plus 2 to the power of W, if that resolves to be a negative value, then we're going to have to go ahead and actually retranslate it. We'll take whatever the binary string is, and we're going to add to it that weight that it subtracted from itself, right? So remember, really the big difference is the most significant bit in an unsigned format is an additive property, whereas in a 2's complement, it's a negative property. So if we want to translate one from the other, we take that most significant bit and we add it back. And that effectively adds our translation. But we only do that when it's there. We don't want to just add it on if it's not there. So this is an example of how that actually looks. Suppose I have X, and I'm going to have the hexadecimal representation of X as B. And so I'm going to give the binary string as 1011. I'm going to give the integer value of that as -5. Okay, so if we do that, then we know that the width of bits is going to be 4. So suppose that I pass in my integer value. Actually, that should be a bit string that I'm passing in. Doesn't matter. I'm going to take that -5. I'm going to add it to 2 to the power of 4. Because what I'm doing is I'm taking the value and I'm going to add it to whatever, it's 2 to the power of whatever our width string is. So that's going to be -5 plus 16, which is going to be 11, which works out back to being the representation of B. So this kind of shows you how by hand we can convert that. And you could double check this by showing that the -1 translates into the max value in the unsigned representation. And again, if I wanted to visualize that same concept, and the reason why I showed you the actual rolled out map in the prior slide is so that you can see the visual representation of it here, where we can do a conversion between the 2's complement and the unsigned side by side. How there's a difference of +16, right, between where this summation is and this summation. The difference is that most significant bit value. And so effectively, what we're really just doing is just range shifting our entire numerical domain from 0 to whatever the width is of our binary string. But the important part to remember is right here, where we have 0, anything that's above 0 stays the same in 2's complement. The thing that gets inverted is when it's a negative. And in this instance, the more ones that are toggled on are actually a lower, go to the max value, right? So our closer to value 0 here goes to be our maximal value in unsigned, whereas as we go down here, it then narrows in to be right above 0. It'll be our 1 value. Okay, and so the same or similar can be true about how we can convert between signed and unsigned in terms of defining that function. In fact, let's jump to it because effectively it's just an inversion of the same thing, right? We're doing the same range shifting, we're just doing it in reverse. So I'm not gonna like we'll use a lot of time to re-explain the same concept. Because I think here we can start to see in illustrations how it gets to be a little bit more interesting. We have our unique binary representations and determining on whether it goes from 0 to 15 versus 0 from 7 to -8, how that actually populates into our encodable space, right? So when we have all ones, that's -1. Our biggest value is actually going to be kind of populated in the middle when our what's the word, MSB, when our most significant bit is toggled on and all the other contributors are toggled off. So you kind of jump in this representation from 7 straight to -8. But that ends up having really good consequences for making the math work. We're going to see that in the next lecture. And so here's just another illustration of still how the mapping works from one set to the other on a per unit basis. Okay, so we talked about the fact there's signed numbers versus unsigned numbers in C. So let's talk about some general rules for casting. C allows the conversion between unsigned and signed numbers. The common rule is that it's going to maintain your bit representation and it's not going to change the value. When an operation has mixed operands, so it has both signed and unsigned, C will implicitly cast the signed argument to an unsigned value. That's what you should be aware of. So unsigned is the default. If you expect it to be negative and for some reason you're mixing values, it's all of a sudden going to become positive. That can lead to erroneous behavior, and you should be aware of that. And in fact, here is the effective C promotion, and the instances that where it's interesting are highlighted by these asterisks. I'm not going to spend time walking through why they're interesting. I'll leave this as an activity for you once I publish these slides, or for you to go look at the textbook and identify why those are interesting. And if you can identify, go ahead and ask either in the Discord or in class, and we can talk more about it. But I think it'd be obvious once you start trying to, with the understanding of what is the default casting operation, what's going to happen. So the last thing I kind of want to talk about in terms of this chapter, or this subsection of this chapter, is going to be we can not only just pass between the types. We spent a lot of time talking about the different numerical sets that are available to us, whether it's the integer set or the whole number set, and how we can translate values, our encodings of a binary sequence between those two different sets. But remember, we also have word sizes as well. The difference between cars and shorts and ints and longs. And there's the ability for us to convert our numerical representation from one word size to another word size. And so we'll just say that converting from a larger size from a smaller size is easy. You can always do that. But you can't always convert from a larger data set to a smaller. You can't necessarily take an integer representation, force it into a short or car, because you might not have enough digits. You might not have enough encoding sequences to actually represent that. So for that reason, avoid that. That's a bad practice to take an int and try to force it into like a car. Okay, but let's talk about casting an unsigned to a larger data type, because it's relatively simple on how we do that. In order to do a unsigned value, all we do is prefix all the way up into the new binary string length with zeros, right? And it maintains its same kind of value. Because remember, it's the ones we care about. Now, what causes a complication is when we want to cast into a larger data type a signed value. But all we do is, what we're going to do is we're going to call a sign extension. We know the most significant bit is going to be the one that starts with a 1. So when we go to carry over to the larger bit vector, we're just going to copy that 1 all the way up in front. And that will preserve our sign for that.
I remember that's two different expansions, one that preserved the sign and one that.
Yeah, it's true. And so sometimes it can be quite useful to handle either of those cases. And in fact, y'all probably went over most of this in MASM then as well, right? Because this is pretty fundamentally important. This is just showing how our binary representation can change based off of the encoding on whether it knows it's going to be a signed or unsigned in terms of memory. In fact, here is a better instance. You'll see this is where it's prefixed with the ones versus zeros based off of whether it's signed or not. You could truncate numbers, but we're not going to do that. We're just going to say that's bad practice. And the last thing is some advice. Use signed numbers. Avoid unsigned numbers at all costs, because mixing your signed numbers and unsigned numbers can result in catastrophe. Okay, so now that I said avoid unsigned numbers, why are they useful? When might you use them? Here's some reasons why. Unsigned values are useful when you're modeling, say, for instance, a collection of bits that aren't intended to have a numeric interpretation. Like if you're just using bits as a collection of Boolean flags, then suddenly that makes sense to use unsigned values. Other times, memory addresses are unsigned. So if you're a system programmer, you got to learn how to use them. And then if you're doing any kind of mathematical packages, you can exploit left and right shifts to do math in very interesting ways. And so unsigned values can be useful in those regards as well. Okay, and so that's it for subsection 2. This is probably enough information we need for me to unlock the next lab. We'll follow up this chapter next lecture, where we'll talk about subsection 2.3, which is going to be our integer arithmetic logic, how we do arithmetic in with integral data types, and then we'll also talk about how we represent our radix floating point numbers. Excellent.
What's lab 2 or the next lab?
The next lab is going to be called Data Lab, and it's going to be, you can think of it as like a lab of small micro puzzles, where you'll be giving inputs and you'll have to process it into different output, and you might even be limited towards the operations you can do to do that. Excellent. Does anyone have any questions before we go ahead and dismiss for, I guess, the week? Excellent. Okay. Well, everyone online, have a good day, and hopefully we'll soon get to material that wasn't part of assembly.